Welcome to the Robust Control in Aerospace Systems course. I will be teaching this course this semester through distance learning. So the lecture videos will be recorded and posted online, and I will be using OptiClass for everything related to this course. I will post the lecture notes here beforehand, and I will post links to the lecture videos. And there will be a forum section where we can discuss your questions and comments about this course. Okay, so let's see. Normally we're scheduled to meet 3 times a week, so these are the lecture hours. We will meet Wednesdays between 1:40 and 4:30 in the evening. I don't plan to do live synchronous lectures. Instead, I will record videos like this and post beforehand, and I will use these sessions for your questions if you have any, or I may prepare some additional example problems that I can show during these hours. But the main lectures will be pre-recorded and uploaded, and I think upload them to YouTube. Okay, well, obviously this is an advanced level controls course, and if you are taking this course, you should feel comfortable with classical and modern control theories. If you are a student in aerospace engineering, if you're a graduate of aerospace engineering department in Matthew, I'm expecting you to have taken these courses we have as elective courses in our department. And the first one is okay, so for a while I thought it was not recording. Anyway, the 384 course is a course in classical control where you see the frequency domain methods for designing control systems like root locus and Bode plot, Nyquist plot, things like that. And the 483 is the automatic control systems 2 course, and the main focus there is on modern control. You basically see the state space methods, methods like pole placement or LQR control, observer designs, things like that. So if you feel comfortable in both of these methods, then this course should be pretty natural to you, hopefully. Okay, there will be homework assignments given approximately every 2 weeks. So throughout the semester, I'm planning to give you 6 to 7 homework assignments. And these assignments will require use of MATLAB. And in particular, you will need to use the control system toolbox and the robust control toolbox. And the homework assignments, homework problems will follow on each other. So that means at the end of the semester, when you combine all your homework assignments, it will look like a project on robust control. Usually, I would give one in-class midterm exam, but since this is distance learning, we cannot perform an in-class exam. And I don't like the idea of making live synchronous exams online. So for this year, I'm not planning to give a separate midterm exam. Instead, there will be these homework assignments, so that will form about 50% of your grade. And at the end, there will be a one take-home exam, final take-home exam for the entire course. And your overall grade will be based on your grades for homework assignments and the take-home exam. So your grade will be entirely based on the work that you do at home. Okay. So you see the semester plan for this course. These are the topics that we will cover. And like I said, you will have the lecture notes given to you before the lectures. Well, I already have the lecture notes written for this course, but I'm planning to improve them a little bit before I post them to you. Okay, so I started rewriting the lecture notes here. So far I already have like 6 or 7 pages worth of notes, and I will be writing them every week and give them to you before the lectures. Okay. Okay, so I think we can just get started with discussing what we will do in this course. So first, I will do a review of control theory before I will start talking about the robust control concepts. Okay, so let's start with a system. Well, if you have taken the system dynamics course from me, then you already know how I define a system. A system is basically defined as an entity with some inputs and some measurable outputs. And the system in engineering, in aerospace engineering particularly, we consider air vehicles as systems mostly. So our systems are either an aircraft, a helicopter, a missile, or even a satellite, but they are mostly vehicles like that. But it doesn't have to be a mechanical system like that. A system can be an abstract system as well. Anyway, we have some inputs for our system, and there are outputs, and obviously there's a relation between the inputs and the outputs. So that means whenever you change something inputs, and you expect that to cause some changes in the output side as well. And we usually divide inputs into two groups. If the input is something that the user can change arbitrarily, we call that a control input. Or sometimes you will see some inputs acting on the system, but the inputs cannot be changed by the user, and we call them as disturbance inputs. Okay, and well, to study a system, obviously we will be using mathematics, and for that we need some mathematical equations that form the relation between the input and the output. In the most general sense, for a system, the relation between the input and output can be represented by an ordinary differential equation, which you can write in this form. And here I'm assuming that our system is a lumped parameter system. Otherwise, if you have a distributed parameter system, such as systems with flexible structures, there will be more than one independent variable, which will lead to partial differential equations in the mathematical model. And those are not systems we will consider in this course. So in our course, we will only consider systems which can be represented by ordinary differential equations. The mathematical equation will be a function of these arguments. Here you have the input signal U and the derivatives of the input signal up to a certain level M. Likewise, you have the output signal Y and the derivatives of the output up to another degree N. And if your system is time varying, then the equation will also be an explicit function of time as well. Okay. In the most general sense, this equation can be a nonlinear function of all of these arguments. But if your system is linear and time invariant, then this function will be a linear function, which means all of these arguments will appear in the equation with some constant coefficients. And in that case, the most general form for this equation will be in this form. Okay, that equation will be all of these terms combined together with some constant coefficients, and these are the type of systems we will study in this course. So when you have such a system, to analyze that system or to design a controller for that system, there are two different ways we make use of this equation. So first one is we take this equation and by taking the Laplace transform of this equation with zero initial conditions, we transform it to frequency domain and we obtain what we call a transfer function at the end. So if you remember that when you take Laplace transform of that equation by assuming zero initial conditions, every derivative term brings an S term. So the Laplace transform of the nth derivative of y becomes s to the power n times the Laplace transform of the signal y. And so you have terms with the output signal y on one side and terms with the input signal u on the other side, and the ratio of these two signals give you the transfer function from the input to the output of the system. And the transfer function for such a linear time invariant system is always in this form. So you have a polynomial of order m on the numerator and the polynomial of order n on the denominator. Here, without losing any generality, we can assume that the coefficient of this term is 1. Unless, if you have any other coefficient here, you can divide the entire equation with that coefficient so that the coefficient here becomes 1 and every other coefficient is scaled by that original coefficient. Okay, and in classical control, we use this transfer function, and we have some nice theories that are applicable to transfer functions that represent single input, single output systems. So if your input is a scalar signal and output is a scalar signal, then you have this single transfer function for the system, and you can design controllers using the frequency domain techniques. You can draw root locus and choose your controller gains by using that, or you can design some compensators, some dynamic compensators to achieve your design goals. So everything is very convenient for single input, single output systems. So this was a positive attribute for classical control. That's why I used a plus sign there. But then there are some disadvantages of using a transfer function as well. And one of the disadvantages is that when you're using transfer functions, you don't get to see everything related to the internal dynamics of a system. So what I mean by that is, if you have an interconnected system, if you have a system where you have multiple blocks forming a big system where you have these connections here, and when you write the overall transfer function of the system, you get the transfer function. However, anything internally happening is lost. You don't get to see what's happening in the system. And I will show you an example of how that can be a problem. So losing the internal dynamics of the system is one disadvantage of dealing with transfer functions. And another disadvantage of using a transfer function is that it's very difficult to work with multi-input, multi-output systems. So if your input is a vector signal where you have multiple inputs, U1, U2, UP, let's say, and then you have a vector output Y1 through YQ. In this case, the transfer function actually becomes a matrix. So you have a matrix transfer function between every input and every output. And obviously, in that case, what you can do with a scalar transfer function, so you have this matrix of transfer functions. So if you have a multi-input, multi-output system, you can't really apply these methods that we use in classical control. Okay, so this is just one way of using this, working with this linear time invariant system. The other one is to directly work in time domain. So instead of taking Laplace transform, you use the equation in time domain, but you don't use the equation directly. To work in time domain, we first write the system in a special form that we call the state space form. To write system in state space form, we define n state variables if your system is nth order, and these state variables are defined in terms of the original system variables, the output variable, and the derivatives of that up to n point, n minus first derivative. Likewise, you need to include the input signal as well if in the original equation the derivatives of the input signal appears. So you define n independent state variables, And you should be familiar with the fact that the state space representation is not unique. In fact, there are infinitely many ways you can write a linear time invariant system in state space form. And that comes from the fact that while defining the state variables, you use a square matrix here. And as long as this matrix is invertible, the definition you come up with by using that matrix becomes a valid state space model. And since you can write infinitely many n by n invertible square matrices, that means you will have infinitely many state space models for a given system. The benefit of having a state space model is that once you have these n first order differential equations, you can write them in matrix form. So you stack all your state variables into a vector, and the system dynamics can be written in first order vector differential equation, like this one. Your state variable x derivative of that becomes equal to some matrix times your state vector x plus another matrix times the input u, and then the output can be written as matrix times state variable plus another matrix times the input variable. So the system is in this form. One benefit of having a state space model is that when you're working with state space models, the internal dynamics of the system are preserved. So when you come back here, so if this is your interconnected system, and if you have state space models written for every block here, when you combine the entire system into one large state space model, every internal dynamics will be preserved in that matrix. So you can easily see if there are any problems internally in your system, you can see those problems in that state space model. And there's another huge advantage, which is that multi-input, multi-output systems can be easily handled using this representation. And the reason being that is if you have your input to be a vector signal, if you have two inputs like that, you simply introduce an additional column into your B matrix. So the only thing that changes in your model is the number of columns of your B matrix is increased by every input you add to the system. Likewise, if you have multiple outputs, if your output variable is a vector signal, then every additional output brings a new row to your C and D matrices. So this form of the model doesn't change. You always work with A, B, C, D matrices. Only the dimensions of the matrix changes. The C, B, D matrices change with the number of inputs and outputs of your system. Okay, but then the state space representation also has a drawback, which is that the nice frequency domain tools that we have for transfer functions are not applicable for state space models. So you cannot really do things like root locus or the frequency domain compensator design methods. You can't really apply them once you have the state space model for your system. As you can see, both of the models that you can have for your system, the transfer function and the state space model, have their own benefits and disadvantages. So depending on what you will do, you may prefer to use one model or the other model. So once you have a model, the things that we do with that model can be categorized into two groups. Well, first, by using that model, we can do system analysis. So in system analysis, we find the output of the system for given input signals and initial conditions. So in other words, if you know the initial conditions of your system and you know what the input signal is, by using this information and the mathematical model of your system, you solve the mathematical model and then find what the output of the system will be. We call this system analysis. The second type of things that we do as a controls engineer is called control synthesis. And in the second part, uh, we want our system to behave in a certain way. And our goal is to find a suitable control input signal to our system that will make the system work in that way we want it to behave. So while doing that, these are the things that we consider. Well, obviously, first of all, we want the system to be stable. Before everything else, we almost always want a stable closed loop system. So that's the main goal in our control design. So we may want the system to be regulated around some set point. So this is called regulation. We want the system to keep in around a certain set point. Or we can want the system to follow a changing reference point. Instead of a fixed set point, we can give the system a changing reference signal, and we want the system to follow that reference signal. We call this the tracking problem. While doing that, we may also want the system to neglect the effects of external disturbances. So this is called disturbance rejection. So whenever there's a disturbance input to the system, we want the closed-loop system to not respond to those disturbances. So we consider these are the main things to consider when designing a control system. So we either do system analysis or we do control synthesis. Okay. And to obtain this control, design a controller, we need to apply feedback control. So we take the output of the system and feed it back to our controller and form a closed loop control system. And only by using such a closed loop setup, we can possibly achieve these goals here. The methods available for designing controllers can be considered in two separate groups. Well, first, from a historical point of view, first, the control design methods were developed in frequency domain because we have more analytical tools available there. So before the computer age, people didn't have the necessary numerical power to process numerical methods. So the analytical methods were the only way to study. And the methods for designing controllers based on frequency domain tools are called the classical control. So as I said earlier, they use transfer function representations of linear time invariant systems. The good thing about using transfer functions is that you can emphasize design trade-offs between performance versus robustness in your controller design. So in other words, you can guarantee that your closed-loop system will be stable, but you can not only guarantee that, you can also consider stability margins. So in other words, you can adjust the margins before your system will become unstable whenever you have some uncertainty in the gain or phase of your system. And obviously, while increasing robustness, you need to give up some performance. So in frequency domain design, you can adjust that easily. So that's the powerful thing about classical control. And the disadvantage is, as I said earlier, we can do that easily for single input, single output systems. But once you switch to multi-input, multi-output systems, then you can't really do that anymore. So as the advancements in technology, systems started to become more complex with multiple inputs and multiple outputs. And at the same time, computers became available. That allowed people to study systems in time domain using state space methods, but without having such nice analytical tools. they started using numerical approaches. And with the computers, obviously, numerical solutions are easy. And that way, multi-input, multi-output systems could be studied in time domain directly using numerical methods. So, and those approaches are called modern control in general. And the biggest advantage we can say for modern control is that multi-input, multi-output systems can be studied in a systematic way, just like single input, single output systems. However, the disadvantage is you lose the easiness of adjusting robustness versus performance when designing controller. Okay, so as you can see, classic control and modern control have their own benefits and drawbacks, and I'm trying to make vertical scrolling available. Okay, so you have the advantages of classical control and modern control, and what we do in robust control is basically we try to combine the benefits of these two approaches together. So we work with single state space models where we can handle multi-input, multi-output systems. Yet at the same time, we use some of the techniques used in frequency domain approach and apply them to these MIMO systems so that we get this advantage of adjusting robustness versus performance in a systematic way. So when you do that, you combine the benefits of classic control and modern control, and the tools that are developed with this approach in mind is basically called robust control. Now let's go over some definitions. So I told you that we usually consider some interconnected systems. So we know what a system is, and when you have several systems come together working in a certain way, we call that an interconnected system. And what you see here on the screen is a general control system block diagram. So let's take a look at this and let's define the signals and blocks that we see here. Well, obviously, the general system, the main system that we want to control, we call that the plant. So this is what we are trying to control here. So if you are trying to control an aircraft, then your aircraft model will be in that block. Okay, and then we use a controller. So this is what we introduce to the system so that the closed loop system will behave in a certain way. In modern systems, the controller is just basically a piece of software. So we have computer-enabled controllers. We have controllers that can read sensor signals, that can process them mathematically, and then they produce the output, and then this output is sent to the actuators through appropriate signals. So this is our controller. And then for the feedback path, we use sensors. So whatever the output of the system is, we use some sensors to measure that output, and then we use the output of the sensor in our feedback path. So if you are controlling an aircraft, usually you at least have some inertial measurement unit. There you will have accelerometers and gyroscopes. They will measure the accelerations and rotation rates of your aircraft. And then they output the values corresponding to those variables, the accelerations and rotation rates. So that equipment will be considered in this part, sensor block. Okay, and then there are some external inputs to the system. So if you consider the boundaries of your system, if you draw a box like that, you see there are three inputs entering this box. One of them is the R input. It is the reference input signal. So this is the target value for our output. Well, you can also call this the set point, desired output, or commanded output. Then there's another signal entering the block diagram in that part. So it adds to the control signal. So if this was an aircraft, the control signals would be the signals to our control surfaces like elevator, aileron, rudder. And if there are some aerodynamic disturbances that create unwanted moments, forces acting on our aircraft, you consider them as disturbing inputs to your system, and this is where you inject those disturbances into your block diagram. So this D represents the disturbance input. Let's also talk about this third input to our block diagram, W. It represents sensor noise, which is unwanted and unknown modifications the output signal may suffer during measurement, transmission, processing, or conversion. So anything that spoils the output signal can be considered as sensor noise. And then this is the output coming out of our block diagram. This is the actual output of the plant. This is the variable which is controlled. And then there are additional signals inside the block diagram. This E is the error signal, which is the difference between the reference signal and the measured output of the system. Sometimes it is also called the actuating signal. U is the control signal, the manipulated variable of the process acted upon to maintain the plant output at the desired value. And the output of the sensor block, we can call this YM, the measured output. Okay, so this is a basic generic block diagram that you can find in many control systems. Okay, so once you have such an interconnected system, it is really important that you should be able to handle these interconnections easily. So let me show you what I mean by handling the interconnections. So this is our block diagram with several inputs, and right now we have one input, but you can define additional inputs, outputs for this block diagram. So let me just clean up this block diagram. And then let me just copy it and move it over to OneNote. Okay, so it's not on the clipboard, so I guess I need to copy it explicitly. Okay, so like I said, if you draw a box around your system, you can clearly see your external inputs and outputs. So there are three inputs, right? The reference input, disturbance input, and the noise input. And there's one output. So assuming every block is a linear system, then you can write the output in S domain as summation of effects of each one of these inputs separately. So that means you will have one transfer function corresponding to each input, and then you multiply these inputs, these transfer functions with the input signals R of S, D of S, and W of S, and the sum will give you the output. And you should be able to write each one of these transfer functions by looking at the block diagram. Okay, so if you have taken these controls courses, then you should be very comfortable with doing that. But let me just show you some examples of how you do that. Okay, so let's just scroll down here. And okay, so first we write the output Y in terms of the three inputs. You basically just take a look at the block diagram, and Y is so let me just remove this part. Y is equal to what? it's the output of the block G, right? So you multiply G with the input to that block, and the input to that block is U plus D. And let me just use capital letters here because these are all functions in S domain. So U plus capital D, okay? But instead of, well, D is an external signal. I can just leave D as it is. But instead of U, I can write it as the output of the controller block, which is K times E. So this is K times E, capital E plus capital D, okay? And I need to keep going because E is an internal signal. It's not an external input yet. I need to write the output in terms of external signals only. And the external signals are three, R, D, and W. Okay, so instead of E, I can write what? R minus Ym, K times R minus Ym plus D, okay? And again, Ym is still an internal signal, and instead of Ym, I need to write H times the input to H, which is Y plus W. So let me just continue here on the second line. Y is equal to G times K times R minus Ym plus D, and instead of Ym, I need to fix this. Let me just. Okay, so instead of Ym, I'm going to write H times capital Y plus capital W plus D. Okay, now everything is an external input signal here. R is an external input signal, Y is my output, W is an external input signal, and D is an internal external input. So I can rearrange this, and I can write the output signal Y in terms of the external input signals to my system. Okay, so Y is equal to D times, well, I use small case letters here, but since these are S domain signals, I should have really used capital letters instead. But anyway, so this is the transfer function. This part is the transfer function between the disturbance input and the output. This is the transfer function from the reference signal R to the output, and this is the transfer function from the sensor noise to the output. Okay, and I can put them in a matrix as you see here. So this is for the output. Well, we can define an additional output to the system, and here we choose the control signal as an additional output. Control signal is here, so I can take this and consider this as a second output for my system, and I can just repeat the same procedure and obtain the transfer functions from these input signals to that output. Okay, and if you do that, so what you should get is these transfer functions for that. Well, you may have a more complicated, much more complicated block diagram than this one here. And as long as you know what you're doing, you should be able to write transfer function matrices for your control system. Okay, so in this course, we will be talking about loop transfer function, and it is not really easy to find a definition for that. I don't think it is mentioned in many other control courses. So let's define what a loop transfer function is. It is defined as the transfer function from the error signal to the primary feedback signal. Okay, so let's just go back to the block diagram. From error signal, let me just change the color of my pen here. So this is the input, and the output is the primary feedback signal Ym. So if you write the transfer function between those two, what you get is called the loop transfer function. And it is, and obviously while writing the transfer function, you assume that the other external inputs to the system are equal to 0. Okay, so let's just write that here. So this is going to be my output, right? I can write that as the transfer function h times the input to h, and input to h is, since I assume w is 0, it is simply y. Okay, and next I can write y as the transfer function g times the input to that block, which is u, because d is again assumed to be 0. And instead of g, u, I can write k times e. And there you go. Now we have the transfer function from e to ym. So we call this the loop transfer function. Let me just show that g sub with g sub l. It is equal to ym divided by e. So these are the S domain functions, and that is equal to h times g times k. Okay, so this is the loop transfer function, and as you see here, it is all these transfer functions around the loop multiplied together. Another important transfer function is the closed loop transfer function, and you should all be familiar with this. It is basically the transfer function between the reference command for your system and the actual output of the system. And we already discussed how to obtain the transfer function. And when you do the when you write the output in terms of the reference command, this is what you get. And one thing I would like to point out here is that I assumed the inputs to the system can be vector signals. That's why I have the identity matrix here. So if you have scalar signals, then you can just use one here instead. But in the more general case where you may have vector inputs, then you need to use the identity matrix here. And then obviously these will be matrices, and you have to perform matrix inversion here. Otherwise, for scalar systems, you can just divide gk with this 1 plus gkh. Okay. So I think we can just stop this first video, and in the next video we will continue with the concept of realizability.